Hello, everyone, and welcome to today's Hot Topics in Computing. I am delighted we have two extraordinary scientists who are also members of the MIT community to educate us on computational epidemiology today. We have Professor Ankur Moitra, who is in the Department of Mathematics at MIT, and he's also a member of CSAIL. Ankur worked in numerous areas of algorithms, including approximation algorithms, metric embeddings, combinatorics, and smooth analysis. But lately, he has been working at the intersection of algorithms and machine learning. And he's collaborating with Professor Elchanan Mossel, who works in probability, combinatorics, and inference. And his research has resolved open problems in computation biology, machine learning, social choice theory, and economics. Professor Mossel is on the senior faculty of the mathematics department, and he has a joint faculty appointment in IDSS. Ankur, Elchanan, please go ahead.
Great, so thanks everyone for logging in. So I'm happy to tell you at least a little bit about what we've been thinking about in the space of computational epidemiology and what we've learned. So I should mention at the beginning that this is a new area for both of us. In fact, how we got interested in this was we were approached by a bunch of epidemiologists about joining a project, and they persuaded us to start thinking about some of their statistical and algorithmic and machine learning problems that they have. Now, this was back in September, so we thought it would be fun to learn a little bit about these problems. They sounded a bit different than the kinds of things we usually work on. And then coronavirus happened, and it changed the way we think about these problems. So instead of thinking about some cute math problems that we could write about, all of a sudden these became much more serious issues. So I'm talking to you not really as an expert, but as an outsider, as someone more from a computer science perspective, thinking about the way that things happen in epidemiology and what the perspectives from sort of more modern algorithmic and computational ways of thinking might lend to these sorts of problems. So let me tell you at least a little bit about some of the background about epidemiology, because it's important to understand where the roots of this field are. So it's hard to imagine, but way back when, back in the 1800s, there were a lot of fundamental diseases that we just didn't understand the underlying mechanisms. And people were dying left and right. So maybe one of the most important cases of this was cholera in the 1800s. So you can see from this new version of a famous map by John Snow of, first of all, the Broad Street pump and all of the surrounding cases, mostly deaths around the Broad Street pump. And when these things happened, they were catastrophic. They took out entire families, and no one really knew what was happening. At the time, there were a lot of theories about what the origins of cholera were, and none of them really grounded in any kind of science. Some people thought cholera was in the air and it was just endemic and impossible to get rid of. But John Snow had a theory that it came from drinking contaminated water. So what he did was, when there was an outbreak in 1854 and there was a rash of deaths all over, what he did was he actually traced through all of these cases and tied them back to the Broad Street pump. In some cases, this was easy. It was something like school children on the route from their home to school. They would pass by the Broad Street pump and they would refill their water. In other cases, it was much more complicated, because there's a story of a mother who was many miles away from the Broad Street pump. There were other pumps that were much closer to her, and it was a complete mystery about how she died of cholera. So in fact, Snow didn't give up. What he did was he figured out from talking to the son that the mother used to live around the Broad Street pump and that she liked the taste of that water more than the other pumps. So whenever someone was in the area, she would ask them to pick up a bottle of it, and she would drink it at home and serve it to her guests, and that resolved one of the mysteries. In fact, what was quite frustrating around this time was that despite the scientific evidence of tracing through these cases and pinning it back to the Broad Street pump, there wasn't a molecular understanding of what was going on, and it was very difficult in general to convince lawmakers to actually try and close the pump or do some other safety checks on it. It wasn't until a reverend who thought that cholera was really the work of God deciding who had been evil that people realized that he tried to show John Snow's work was not the correct explanation. And he actually pinpointed that the reason that the pump had been infected was because there was a nearby sewage dump area where a mother had dumped some of her dirty diapers and there was a leak in that sewage that actually led to the water becoming contaminated. So this is by no means a full history of epidemiology. After that time, people spend a lot of time identifying new diseases, tracing the mechanism of spreading, even trying to understand what are the underlying bacteria or other factors that lead to it. So one of the things which has really changed the game within epidemiology has been the advent of more DNA technologies to peer deeper into what the underlying mechanisms are. So this generally goes under the umbrella of molecular epidemiology. And if you think about what the DNA revolution has offered, well, it allows us to look into specific diseases and understand what are the chemical pathways that these things take to cause infections. That gives us some idea about what are the potential treatments we could take instead of taking some blind approach to looking for cures. We can look into what kinds of molecules affect it and what particular genes and try all sorts of therapies. In fact, it even gives insight into some of the original questions of epidemiology, because by tracing things like the genetic structure and how they mutate, you can actually give new insights into the transmission. So what's depicted here on this screen is actually from a paper which studies the transmission of tuberculosis. And through genetic understanding, they can distinguish between cases where there's one rash of transmissions and the case where the tuberculosis was already present but was reactivated after a very long time. So it adds very much a piece to the puzzle in trying to trace these diseases. Now, I should mention that what we're going to try and do is, because some of these areas are new to us too, I want to offer some thoughts, at least high level, about what are some of the new ways that statistical and computational thinking can change the types of questions that we can ask. So I'm sure everyone's been following all kinds of things on the news because it's a little hard to ignore these days. But one of the things that I've certainly been wondering about that can be posed potentially as a nice statistical problem is you see that some of the ways that governments have been dealing with coronavirus, especially early on, is through contact tracing and trying to understand when there are community transmissions and whether we can fully identify all of what those are and stop the spread. But one of the things which isn't obvious is, what is the tipping point at which we should no longer be trying to try these strategies of tracing all of the contacts, and at what point is it hopeless? This depends a lot on what kinds of information you can compel people to disclose about their contacts. There are cases, for example, in Connecticut, where a single party that someone had for their 40th birthday led to what's called a super spreading event. And for a long time, the small town tried to trace all of the different contacts until a couple days later, someone who'd been at the party admitted later on, and he waited so long because of some of the social stigma of being responsible for it, that he'd attended a party a few days after with 400 different guests. At that point, they completely gave up trying these strategies of contact tracing and shut down the schools almost immediately. So let me switch over to Elchanan, who's going to tell you some of the beginning parts of how exactly we start to model growth, moving from simple ODEs to more complicated models.
So yeah, maybe let me start by two comments about, even in parallel of the historical perspective that Ankur presented to what we're seeing right now. So if you think about the Broad Street pump situation, and you think about the Wuhan market situation, or even policy decisions in the US, you see the parallels where the people who hunt for the disease already know something. They don't know how to prove it, scientifically 100%. But the policymakers are very reluctant to do anything because of financial interest, because of the fact that they don't want the public to panic. And unfortunately, we see this in multiple scales in the current outbreak. I also wanted to mention that the molecular techniques that Ankur mentioned played an important role even now in trying to identify how long have been the disease rampant in the US, and the use of phylogenetic techniques by people in the University of Washington was one of the main tools that led to the conclusion that the disease in fact has been in the community for a very, very long time. So I mean, we are still using this molecular epidemiology techniques even in this current disease, and this is of course related to the policy questions that Ankur mentioned. Right now that we know that it's rampant or somewhat rampant, we know that it's somewhat widespread. This leads to the policy decisions that Ankur and I are both fascinated by. When do you give up? The question, when do you give up and decide this is going to eat everybody? And the question, or almost everybody. And the question is, how do we do it in the way that's best according to some optimization criteria, versus is there still a chance to try to do what China or Korea did, which is to stop the disease by tracking people. So yeah, so let me go to one of the basic model, one of the simplest models in this area. So we'll talk, you know, at a very high level about more sophisticated model, but this model or models very, very similar to this model are still used in order to inform policy and make predictions. This is a very, very simple differential equation-based model in which there's the population is divided into 3 types. They are the susceptible, the people who can get infected but haven't been infected yet, the infected, the people who are infected, and the people who have already recovered. There are many things that are missing here, in particular people who might die from the disease. Let me go over the details of the model. There's a disease. At some rate, people are being infected. This is decided in the first equation. This rate is beta. Among the infected people, some of them become susceptible. Some of them some of them recover, some of them do not recover, and this is decided by this parameter beta and gamma. And what's easy to see from this picture is at the beginning, this is what also we're seeing at Corona, the disease, which is, I believe, the red curve, goes exponentially, and then it goes down, right? So that's the basic dynamics of many diseases that spread. Many diseases do not actually spread, right? They start spreading and they immediately die out. But for the diseases that do spread, that's often the dynamic. And what you see, hopefully, in the yellow curve is the number of people who have recovered and now immune to the disease. So in this model, again, nobody died. So this gets to the full population. And the parameter of interest that, and you may see it discussed a lot in the literature regarding Corona, is this parameter R or R naught, which is how fast is the exponential growth of the disease. And you shouldn't really think about this parameter as an absolute constant coming from nature, like one of the physical constants. This is something that's very, very much dependent on the environment, or the country, or the community where you are. And it's also very, very much dependent on policies. And indeed, one of the ways to think about policies is like in the idealized situation of applying interventions, you want to get R naught less than 1, because if it's less than 1, then the disease will die out. That's the ideal. But even the policies that people are considering right now, the goal is maybe just to get R naught a little lower than the value that people cannot really estimate. You know, the estimates go anywhere between 1 and 4 these days. It's really, they really vary a lot. But even if you lower R by a little bit, maybe you give more time to the hospitals to get prepared. Maybe you get buy more time to develop vaccinations and so on and so forth.
So just to add in a quick comment too. So one of the difficulties, I mean, there are a lot of difficulties in taking these very simple models like ODE-based things and trying to fit them to data. So in fact, we see, you know, already in the US that, you know, something that really affects the growth of these curves is also changes in the testing policies about who's, you know, who's allowed to be tested. We can see that initially when coronavirus started, there were extremely stringent criteria that you had to meet. And they were also focused on trying to understand the community spread. So if you were in various risk categories, then they would test you if you had various symptoms, but also if you'd been in contact with someone who had tested positive. But of course, being in contact with someone who tested positive meant that that person also had to meet the criteria of being testable. So it was very difficult to see, you know, actually these types of curves being present in the data, especially because as you change the policies about who's allowed to be tested, you can see these wild ramp ups that don't actually have to do with a change in the number of people who are infected or the growths or the lack of efficacy of the different policies, but just the different ways that these things are being reported. So one of the other things to keep in mind in terms of open questions is that it also makes sense to try and understand ODE types of models like this in cases where we work with statistics that we have a bit more confidence about. Like maybe instead of the statistics about how many reported positive cases we have, we can put a little bit more faith in the number of the statistics of how many people actually have been admitted to hospitals, because those actually don't vary quite as much what the admission criteria are across different states, at least at the moment.
So, you know, when somebody in the modern age of our time sees such a simplistic approach, you immediately say, oh, I can do much better. I can model the disease much better. And indeed, a lot of the modern work in this area is based on modeling, which is very, very data intensive and very, very, I mean, there's art to this model. So these are what's called multi-agent models. And the idea is that we don't just want to use some parameters, some simple parameters, beta, gamma, and so on and so forth. We want to model better the fact that there are different kind of people, different kind of communities, different kind of interactions. And the hard part of this modeling is to model people interaction, right? So most of the diseases come into play by people interacting with other people. And the question is, how do you model the population-wide interaction of population of, say, 200 or 300 million people? And what people do is they try to use various kinds of data. I mean, I think in the last 30 or 40 years, it was mostly census kind of data, but also information from traffic sources about how much time different kind of people spend with different kind of people and who are these people that they spend time with, right? So we want to estimate the interaction graph of various people. How many people do you meet a day? How far away are you from them? When you are close to them, for how long do you stay close? And this is very important in trying to model the spread of the disease, especially when we talk about respiratory diseases. The other part of the modeling, which is typically easier because it just involves an individual or the statistical behavior of an individual, is to estimate how does this disease develop per individual. How long is the incubation period? For how long are you sick? For how long can you infect other people? And for this, often just by observing a large number of patients, you can get pretty good estimates for that, even though there's a caveat, right? For like a virus like the corona, where it seems like many of the patients get the disease in a way that's very, very mild or not noticeable at all. It's actually estimating how many people have this kind of disease and how long are they sick in this kind of mode and how many people can they infect in this kind of mode. That's something that we don't know because there isn't most of the data that we get is skewed toward the patients that get the disease in the stronger form. And then once you have this model and you believe this model, you say, okay, now here's what I'm going to do. I'm going to decide that every second high school is going to close, and I'm going to close all kindergartens and close the Whole Foods and just leave the Trader Joe's open, and then I run my model and I can come up with a policy recommendation. Huh? And a lot of what we're seeing, and we'll see it in the next slide where we talk about the Imperial College paper that got a lot of traction, is to try to evaluate the efficiency of various interventions using these models. Now, for people like me, who've been in the business of networks for many years, we know that the main challenge in this is that these models are very sensitive to the parameters. And even if you know you get a lot of census data, it's actually very difficult to get a good evaluation of how long do you spend in proximity to other people and what the actual distance is in meters. And even if you know the actual distance in meters, it's really important if you're coughing into your elbow, you're coughing into your hand, or you're coughing into the open air, right? So there's a lot of parameters that eventually people just eyeball. And the parameters of this model, these are very large networks. There's a lot of interaction, and people who've heard the word phase transition, they undergo very dramatic phase transition depending on this parameter. So this model sound like a very good idea because they include all of the data that you want, but in practice, the efficacy in actually predicting what will happen is not so good, and people in the public health community are very well aware of that. And what they do is more like, you know, we know that this is not the model, but let's play with various policies and see what kind of pictures do we get, and maybe it will inform us. So it's a little bit like the models in economics. People in public health don't believe that this is a very good model. They don't believe this is the kind of predictive model that we will use in statistics or in machine learning. They don't believe that the quality is good enough. As a result of that, or compounding that, is the fact that these models are not publicly available. I think maybe one of the reasons that once you start playing with them, you realize there are so many parameters that people just decided to fix to some value with no reason, and that if you change these parameters even by a little bit, then the model behavior completely changes. So it's not really open science. It's more like an art. I mean, I don't know if fortunately or unfortunately, but these sophisticated models have very strong impact on policy, even though the scientific base of this model is actually pretty weak.
Yeah, so just to add to that and to emphasize, so the way that you're talking about, one of the most fundamental things is this interaction graph. So this Imperial College study you need to take census data and somehow figure out what's the distribution of how much time people spend on public transportation. Now, this is an extremely constrained problem. So it's open to interpretation how exactly you figure out these kinds of things. One thing that we haven't really seen too much in the literature in comparison to other fields that use a lot of network ideas underneath them is that if you compare to something like statistical physics, you're also interested in macroscopic properties of the underlying network. So you don't care about the actual individual atoms, but you want to understand what kinds of temperatures you have different magnetization properties. And what's important there is that actually many of the nitty-gritty modeling assumptions you make end up being abstracted in simpler models that capture the rough dynamics of what the model is doing. So I think there's not so much of an understanding in some of these multi-agent systems of, first of all, how robust are their predictions, because these models aren't even public, so it's impossible to play with other people's models or reverse engineer how exactly you created the interaction graph. And it's also not so clear whether you need to go to this level of sophistication if at the end of the day, having that many different modeling parameters just confounds the issue of trying to understand what the macroscopic properties are and what the impact of policy is on those properties.
So here is the table that Ankur and I like the most from this Imperial College study. Unfortunately, I cannot see the last column because I see the windows of the people, but this table tries to evaluate different interventions in the disease in terms of closing high school, who safe isolates, do sick people stay at home, and so on and so forth. And I won't get into the details of this picture. I think Ankur and I, like many other people, were mostly interested in the question of how effective is an intervention of the form you just tell old people, maybe like me, to stay at home, and you tell young people, like most of the viewers, you can go outside and develop immunity. And then once you develop immunity, I will go out and be happy, right? So that's a question that, you can see discussions over the pages of the New York Times and other places. But so this maybe is related to the last two columns of the table. You can look at this a little bit later. But what I want to point you to is that we really don't have a very good of the R naught before intervention, what you see in the leftmost column. So there's 2.4 and 2.2. The range of estimates that we have for R naught is much wider than the interval 2.2 to 2.4. And the impact in terms of the number of deaths and hospitalization and so on and so forth is huge, right? So this is just like a huge impact. This is a parameter that we don't really know. So you have to run this model with these two parameters, in addition to the other millions of parameters that are under the hood that both Ankur and I mentioned, and you can get dramatically different results, right? So that's just to tell you, the kind of very, very idealistic assumption that people make and their limited application in deciding on policies.
Great. Okay, so I want to also talk about some of the ways that more traditional computational thinking can help in the picture, but also what are some of the pitfalls and what are the things people have tried in the past. So one of the big questions right now is also, we basically don't understand most of the statistics about the coronavirus, right? We don't understand what number of people are actually infected. Most experts predict that if you take some place like Massachusetts, the number of actual infections is probably somewhere between 5 to 20 times larger than what's actually being reported. And in fact, over time, our understanding of these statistics might even get worse, because there are a bunch of places like New York and California where public health officials have actually advocated that maybe we should reduce testing because maybe we should only be testing people for whom the outcome would actually change their treatment plan. Now, the reason why they're suggesting this is because there's such a drastic shortage of personal protective equipment that this is now starting to drive some of the decisions that we make. So every time someone gets tested, you need to throw out that entire set of PPE, and then there's just one less patient in the future that you'll be properly equipped to be able to handle. So one of the things that I think is very interesting that's not really discussed in some of these models so far, actually let me transition backwards, is first of all thinking about issues like, if I don't fully understand what the growth is of the number of infected people, then how much does that hurt my policy implementation? So you can see, for example, from the Imperial College paper that there is some understanding that when you actually institute the policy of quarantining people, well, it depends on how well you time it with the peak. So if you time it really well with the peak, then its ability to flatten the curve is much more multiplied than if you mistime it. And one of the things that we don't understand is, for example, if we lose information about tracking how many different infections there are, how much of a price do we pay in terms of the efficacy of our different policies? In fact, a lot of these models also don't take into account some of the other parts of the picture that are really fundamental to understanding what we're actually going to deal with. Sorry, Daniela?
Ankur, we have a few questions about the slide.
Oh, sure.
We have some of the viewers would like to better understand what the numbers are. And so I wonder if you could take a minute to explain the numbers in the table.
So Elchanan, you want to go for that?
I actually don't have the paper in front of me, but a big number is better. This is a reduction in hospitalization or deaths and so on and so forth. Right? So I forgot, I think this is I don't remember if it's this hospitalizations or deaths, but I think that 67%, for example, means that this is 67% less deaths than if you would not intervene at all. So the green numbers are big numbers. This is how much less of the bad effect will you have, given the intervention that's written on top. I think, like, for example, the last two columns are closing school, people over 70 self-isolating, and one of them has closing of schools. The first one is closing of high schools and elementary schools, and the second one does not, right? So this is an example of a column, right? So, so you do that, and it says, actually, the left column says peak beds, right? So these are the first two items are peak beds. How many hospital beds will you need? So a number like 18% means you will need 18% less than what you would need if you were not using any intervention at all. 69% would mean you would need about 70% less beds than if you would not intervene at all. Right? This is like the 8th row of this table.
And also, I think it's worth mentioning there's some parameters that really, I mean, are so widely, it's not clear how exactly you would set them, that are a really important piece of the picture that are not a part of the study. So for example, the focus here was on the number of total people infected and what the peak number of beds in the ICU you would need is, but they didn't actually explicitly model things like when you were over capacity by how much does that affect the mortality rate?
Got it. One more question about the slide. If we don't know are you saying we also don't know gamma and beta?
Indeed.
Yeah.
Yeah. I mean, the actual model, again, even in this study, and definitely in more, right? So in this, let me just say, I mean, this study uses the more sophisticated multi-agent modeling, right? So there isn't just a gamma and beta, right? The parameters will be different for different individuals depending on their lifestyle. And similarly, the mortality rate would be different for different people depending on the demographics, their age, having other diseases, and so on and so forth. Right? So, but even in the simpler model that we described at the beginning, that people do use in order to simulate various policies, the values of gamma and betas and other relevant parameters, maybe gamma and beta for different age groups, are not known.
Right, and just to point this out, right? So gamma in the original SIR model is what the rate is of people recovering. So we don't even have any idea how many people are actually infected. There's plenty of belief that a lot of the spread is due to asymptomatic cases, which we're not even seeing. So that very much affects gamma. So, but there is hope in trying to leverage some types of data sets that are more complete than others to extrapolate some of the information we're missing on the larger data sets. So if you think about, for example, the Princess Diamond cruise or South Korea, where there's much more widespread testing, some of the ways that people are getting these numbers about the number of actually infected people in Massachusetts is by extrapolating things we see there about how many people have, very bad symptoms, how many people are asymptomatic, and trying to apply this to the partially observed data that we see, in the US when we don't have this kind of rampant testing.
And again, there's more biology in the background, right? They're starting to deploy antibody testing, in which you can also test for people who have been infected before and recovered, right? So obviously, as time moves on, we'll get more data of different types.
Okay, two more quick questions about the slide, please. One question is about modeling uncertainty. What are the current approaches, and would something like Bayesian estimation or inference techniques be useful?
Yeah, I don't know what did they do in this study, but I think the people who do this work, people who are trained in public health, are actually pretty mathematically sophisticated. And they do know that their models are very sensitive to assumptions. And they do know that if we will start to do some serious robustness, they will get very, very different behaviors, as we see in this table. So I think it's really, really different than the kind of science where you get, where you care about a prediction where you're accurate with probability 87% versus 88%. The spectrum here is much, much wider. And people in the field, who've been modeling this kind of phenomena have had these experiences for very long, and they are very well aware of that, right? So I think one of the ways for them to think about it is, one, to compare different policies just to see which one is better and which is not in different parameters, but not as a predictive tool, like saying, maybe if in various settings we're trying something, this is better than that, then it will also be better in the real life situation. So that's one case where people do it. The other situation where people do it is whenever you have a very complex system that you don't understand and you want to control it in some sense, it makes sense to make some assumption and just follow the behavior for a very, very short amount of time and then adjust all of the parameters and so on and so forth. So I think that's a little bit of this and a little bit of that.
Yeah, and just to give you a sense of some of the other parameters in these types of studies that are really sensitive in this way. So there's another parameter in here, which is, when you institute the policy of, let's say, quarantining, then there is a parameter in there, which is what fraction of the population complies. Now, in the imperial study, it was 75%. Now, this type of parameter, it's not so clear how exactly you set it. It's not so clear how it depends on which different demographics you're talking about. It's not so clear how it varies from country to country. So a lot of people right now are looking at this, imperial college study to try and, understand whether it's reasonable, how robust are its predictions. In fact, there was a nice Reddit thread in which Bill Gates weighed in with what the Gates Foundation thinks. And one of the points that he brought up was, well, it also doesn't explain what happened in China, where they were actually able to curb the growth of coronavirus. So there's a lot of, sanity checks and eyeballing of parameters, where in these types of models, if I play with something like the compliance rate, you can actually see wildly different behavior. So it's just something to think about.
There is a flurry of questions. I will ask one more and we'll leave the others for later, so you can go on with the talk. And one question is, how does R naught relate to the doubling, to the days to double?
So yeah, R naught is so one is the log of the other, also so on and so forth, right? So if the day to double is x, so when x to the R naught is equal to 2, then x is the number of days to double.
Got it. All right, please go ahead.
Okay, so let me also tell you about, because computational epidemiology really has many different facets. So what we talked about so far were some of the roots of epidemiology, and you can see already that there are many different types of problems you can study there. You can study these contact tracing types of inference problems. You can study these modeling types of problems about trying to understand the growth as a way to check the efficacy of different policies. But there are, now these days, people are also trying to think about what are different sorts of data that we can leverage that, can help complete some of the puzzle. So I want to give you at least a little bit of a sober look to these kinds of things, because they're both very good and also not necessarily good. So there was a famous example of Google flu trends that you can see this curve right here. There were actually two instantiations of the algorithm. So there was the 2008 flu trends algorithm, and there was the 2009 flu trends algorithm, which ran for quite some time. And the basic idea is that Google has access to this amazingly rich source of data, which is search queries. So you can get some idea of how many people are worried about the fact that they might have the flu by searching, for example, for flu symptoms or other types of things like what are good remedies, should I be running a humidifier, that kind of thing. So you can see that this 2008 flu trends algorithm, when it launched right at the left end of this curve, it was quite good at tracking the actual flu rate compared to the CDC data. But then towards the end, it stopped tracking it quite so well. And then they had this update to their algorithm in 2009, and now it looks even better because it tracks the peaks quite well, other than this blip in 2012. And then all of a sudden, the thing went completely off the tracks in 2013 to the point where Google cut the flu trends algorithm, and it's no longer something that they actually run. So it's still something that people try. We don't all have access to Google search queries, but something that people have been trying within computational epidemiology is to use things like Twitter. So there are some interesting NLP types of problems that people have had to solve en route to doing this, because they want to distinguish between tweets which are about individual people saying that they feel sick versus people generally talking about the flu. And this is a big problem around spikes, where all of a sudden you'll have tons more people talking about the flu than will necessarily have the flu. And this could be one of the confounders with what happened in 2013. So there is some kind of hope for trying to leverage these different sources of data. But so far, a big problem has been that it historically can track it well sometimes, but when you have these big spikes, things all of a sudden go out of whack, and then we're just spewing out this incorrect data. So some of the other big data approaches that people have tried are they can use things like mobility networks from GPS data to try and figure out all of this fine-grained detail about who actually has been in contact with other people and at what distance. Now, a lot of times when people do this, they do it in very small scale. So there were some instances where people did this within schools to understand the spreading. One thing that they do is, as Elchanan mentioned, there are these very complicated multi-agent models that people use to try and model the spread of disease. And so what people sometimes do is they use these mobility networks that they've learned from data to try and check, against the actual multi-agent models that they've had and see if they're reasonable. So are there the right degree distributions, the right number of triangles, these kinds of network statistics to at least give some proof of concept that it's getting, roughly the right network structure. But it's, of course, a very complicated thing because you don't really care about all of the network structure. You care about the parts that have an effect on the macroscopic properties of what you're observing. Now, people also can use this GPS data in principle to try and to trace the spreading of diseases through contact networks. And here there's a big difference as you vary from country to country about what is and is not feasible. So in other countries, particularly in Asia, we've seen that the governments have been able to force people to actually disclose who they've been in contact with through check-ins, through their phones, this kind of thing. But right now, this isn't actually something that we can do very effectively in the US to try and trace contacts this way. So it is one thing to think about. Now, as I mentioned, there are actually many different problems that you can study besides just these modeling types of things. There are also some interesting sensor questions about how exactly you can detect early spreading. Now, we see this already with the coronavirus, that it popped up in some communities much quicker and ramped up much quicker than in others. So, for example, West Virginia was the last state in the country to actually have a positive confirmed case. And meanwhile, New York City was exploding and continues to explode in the number of positive cases. So what you can ask is, in some communities where you haven't yet seen this kind of explosion, but it's happening in neighboring areas, are there good ways to try and detect early onset of pandemics within different areas? That tells you something about when is the right time to time some of the interventions that you're trying, like closing down schools. So one of the first famous studies of this is through what's called the friendship paradox. It's a beautiful mathematical and rigorous statement, which is that if you take any graph that's connected, where the nodes do not have all the same degree, then if you choose a random node from the network and look at its average degree versus you choose a random node from the network and choose one of its random friends and walk along the edge and ask it how many neighbors it has on average, that's actually strictly larger. So this is called the friendship paradox. It has the really disappointing message that your friends have more friends than you, but that was the mathematical statement behind it. So there's some really nice work of Christakis and Fowler, although there are a lot of questions that people have about actually reproducibility for these things, where what they did was they took a group of 400 students from Harvard, and they wanted to use the friendship paradox as a way for early detection of the flu. So they took those 400 students and they asked them all to name a random friend in Harvard. And they took that group of 600 something people who'd been named as friends, and they tracked how early on average they got the flu versus how early on average the people from the original group got the flu. And what they found was that this idea of using the friendship paradox supposedly allows you early detection of the flu by as much as 1 week. Now, there are a bunch of caveats that people have, so you should take this with a grain of salt that not all of these things have been fully reproduced. But one of the other things that people have studied are other mechanisms to place sensors socially to understand early detection. So there are works like graph dominators, which are a very worst case and combinatorial optimization viewpoint. So the way that these things are quantified is that for all starting nodes of where the infection is spreading from, you want to have a small subset of nodes that universally acts as a very good early detection, regardless of where that initial seed is. So these things end up in practice on big networks, end up being quite large themselves. So it's not really so clear feasibly how to scale them. But it's also not so clear whether you want to formulate them in some kind of worst case sense, because we don't necessarily care about the worst case over all possible initial starts for the seed. But generally, as infections are spreading, we do have some idea about where are the hotspots. And we might want to seed some kind of sensors so that we can detect it when it spreads to other communities that are not currently hotspots. So this is some simulated data where people tried out these dominator trees, and they showed that, again, much like the friendship paradox, you can get early detection from the dominator tree compared to this ground truth of when the infection is actually spreading. Now, there are other sorts of problems that you can study within computational epidemiology. Like one of the other classic problems here is you might want good algorithms or approximation algorithms for distributing antidotes. Now, for those of you who come more from a computer science perspective, this might be very similar to some types of problems you've seen within viral marketing, where you want to figure out what are the most influential nodes to offer deals to so that it spreads as rapidly as possible across the social network. But one thing to keep in mind is that distributing antidotes is not the same. And in fact, even the way that you formulate the question ought to be quite different. So some of the seminal works in these questions about good approximation algorithms for distributing antidotes, like this Anderson and May paper, what they do is they assume that the entire graph is known. But really, this is a totally unrealistic scenario setting, as you can see from the fact that we don't have a good understanding of what the interaction graph is. So some of the things that people have been working towards in this area, especially people like Elchanan, is trying to understand what we can do in the face of uncertainty about the graph. Are there good active learning algorithms for querying a small number of nodes or connections to get some idea about how exactly we should seed viral marketing or alternatively distribute antidotes? So let me let Elchanan take away and add some more discussion on that point.
Yeah, so this is still speculative. As Ankur mentioned, I think people in public health have noticed that distributing antidotes to high degree nodes makes a lot of sense. I think also in the context of Corona, it's not just where you distribute antidote, it's maybe also who you test and who you test either for the disease or for antibodies. One of the things that Ankur made me think about just today, so I don't think there's any concrete research here, is to try to think about ideas that we used in the context of viral marketing, of how do you do viral marketing where you don't know the graph. I think, unfortunately, our algorithm is something like you choose some disease, you spread it many times, you see how many people and which people it infects, and then you decide who are the central people in the network. But it's possible that something like that can be done if you simulate the disease, using an app on the phone or something like that, right? So there's definitely some venues to test ideas like that in future research. So as Ankur mentioned at the beginning, I mean, Ankur and I were very excited to join this effort of, real experts in this area of epidemiology. And there's an expedition proposal that was just approved by NSF about computational epidemiology. And one of the goals, and one of the reasons we are very happy to give this talk is that we really want to establish a community for this area in computer science. And I think this is obviously a very good time to do that because everybody is thinking about it. I think a harder goal, especially in the context of the current proposal, given that there are so many different models, there are so many different players, the models are all bad. I don't think that Ankur and I know some amazing models that will decide everything, that will determine what's the right policy to take. But maybe at the longer run to play some, by coming up with better models that are more robust, more precise, more quantified, impact policy, and informed thought leadership. And so this is a very big grant. Many people from many institutions, many of them working in biology, in public health, The two PIs are Madhav Marte and Anil Vulkanati.
Great, so we'll end there. I'm sure there are going to be a bunch more questions, so I'm happy to take them and maybe answer them.
Thank you so much. This was awesome, very, very informative, and congratulations on the expedition. What a timely topic. And we are so happy to have experts with us. Okay, so I have a lot of questions, and I'm going to try to scroll through the chat.
Maybe somebody already corrected me about my formula for doubling. So my formula for doubling wasn't quite correct, but it really depends on the model, right? So the relationship between R naught and the time for doubling is very model dependent. So thanks for the person who told me that for one model, this is not the right formula, but it really depends on the model. There's some relationship, it's some sort of exponential growth. So what I said is, sort of correct depending on the model.
Also related to R, we are wondering whether different communities have different Rs, and is this taken into account in your models?
So within the simple SIR types of things, there's the capacity just to choose different R naughts, but I easily imagine there are different R naughts, especially when you talk about different policies like quarantining. At the very least, different communities are going to have different compliance rates, which very much affects a macroscopic R naught that you get out of things like the Imperial College model.
All right, next question. What sort of robust optimization techniques are typically used in public health?
None.
Okay, so this is an area where we can contribute, right?
Mm-hmm.
Hopefully, again, I think the models are very, very sensitive. So, it's at least for short time predictions and decisions, we might be able to do something.
Yeah, I think, so, I mean, you can certainly think about things like a la robust optimization, which policy is going to be the best in a worst case sense over the different allowable intervals your parameters could be. Now, the original Imperial College stuff, you can look at it that way too. In fact, you can look at the tables that we presented, at least one example of that, and you can ask, is it robust to the different choice of R naught? And you can ask for what's the most robust policy. I mean, the truth is that none of them are particularly robust because as you change R naught, the actual impact of the policies is wildly different. So one of the things that I do think is interesting is instead of just thinking about static policies like from now on, everyone will self-quarantine for the next 6 weeks, you can also try and think about dynamic policies that might have different self-quarantine rules depending on the different percentages and different communities of how many people are infected. Now, one of the real problems with deploying that is that we just don't know what is the number of people who are infected in different communities. But there's also the capacity that adaptive policies might quantitatively end up being more robust. And usually robust optimization asks this, this question about what is the most robust, but one of the questions which is also important is just how robust is that to the uncertainty in R naught? And that's one of the sticking points is that so far the answer is not that robust.
And maybe a different perspective on that. I think one of the issues with adaptive policies that we have to take into account is compliance or just understanding of the public of what they're supposed to do, right? So it could be that if we tell people you stay at home for the next 6 weeks, they will comply more, but could also be that they will be much more excited if every day there will be a radio announcement by the president saying, today you can go play out, and then the following day, oh, the next 2 weeks you have to stay inside. It actually may be that, we have to take into account that, there is the possibility that more dynamic policies will result in either more or less compliance.
It seems like the ICU data would be very useful, at least for COVID-19. What's in the way of getting the ICU data?
To me, it seems like in the US in general, it is very, very hard to get data. It's very hard to get data about how many people are tested. It's very hard to get data about hospitalization and I don't know why, but I agree. I completely agree with you. Even at the community level, how many people have respiratory disease right now? I think all of this information is super relevant. I don't know that it's tracked in the US. I don't know if it is tracked.
So, I mean, right now, some of the best data sets are, Italy has a bunch of data sets online. There's the Princess Diamond data sets. But certainly if we had access to the US data sets and also understanding why people were admitted, like, if some of the rules about admission were actually clarified, then it could be a lot easier to try and back out from the censored data where we only see a part of it, what's actually happening in at least a somewhat more meaningful way than the guesstimates that are sort of floating around in the news right now.
I guess the one thing we have in the news is the number of deaths. And I wonder if you can elaborate a bit more on how we can use that to get better models and better predictions. You touched a little bit on that, but can you tell us a bit more?
So definitely you could use things like, deaths. So one of the things that, so certainly if you look at the US data right now, we have information about the deaths, but one thing to keep in mind is that the mortality rate, the number of deaths divided by the number of positive cases, obviously that's not a good estimate because we're underreporting the number of cases because of lack of testing. And that actually varies on a state-to-state basis depending on how easy they've made testing available. But one of the other things to keep in mind is that sometimes the death rates lag in the sense that people are admitted to the ICU and then it can actually take a little bit before we find out whether they can weather the storm or not. Now, I mean, I've seen some statistical analyses of, for example, comparing South Korea to Italy. And South Korea, we have much more widespread testing. Certainly, people are wondering a lot about why the mortality rate is so high in Italy. And some of the explanations we've seen are the skew in terms of the population, how much older it is in Italy. But this alone doesn't explain very much of the picture because the fraction of the population that's above 80% is only overrepresented in the reporting data by a factor of 2 compared to what it is in the baseline population, which is not a giant amount. So it actually, in principle, should not be skewing the death rates by as much as the ratio that we're seeing in South Korea compared to Italy. There have been a bunch of other conjectures about the prevalence of smoking and all kinds of other things. But yeah, I definitely think this is a great way to go, is to try and understand from the data we have, first, if we can have more insight into how exactly it was collected, what's the mechanism, what are the different rules for how exactly we decided who was admitted and who we're going to test, then there's much more scope for correcting across different populations and actually trying to understand what the heck is going on.
But it may be that the right thing to do right now is just to do the basic public health work of testing people random, not just more, but maybe even randomly, and testing for antibodies as randomly as we can to get a better feeling for what is happening with this disease. And my guess is that this will happen in the next few weeks anyway. So we'll get a much better picture of how many people were exposed in the next few weeks, and we'll get a much better picture of what's going on.
So there is a comment from Pete Solvitz I would like to share. And he says, Dr. Leo Selly and in Roger Mark's lab and an ICU doctor at Beth Israel are trying to get real-time ICU data. And there is a focus to enable real-time ICU data, at least from Beth Israel.
That's great.
That's great to hear. Yeah.
But there are, but I think that to the extent to which we can make the medical community aware of what we could do if we had access to their data in a more timely way, maybe in this time of crisis that will become available. I will make a comment and then ask one closing question to both of you, since we're getting close to the top of the hour. The one comment I will make is I see a lot of questions from very enthusiastic students who would like to learn more and join the field. I wonder if you'd be willing to share some resources that we could post in addition to the video of this talk for the students to get access to. Would that be all right?
That sounds great. In fact,
yeah.
Maybe one thing we could do is we could also open it up so that people could post other resources too.
Yes.
Because I find that people know all kinds of different pieces of the puzzle. So personally, I mean, there's only so much news I can read with the same statistics being regurgitated over and over again. but thinking about it academically is a good kind of antidote, and actually reading papers that try and dig deeper than just understanding, you know, at very cursory levels what's going on is, you know, great.
Okay, so here's my question for both of you. Given where we are today and what you know about computational epidemiology, what is the best case scenario and what do you think will happen more realistically?
I'm happy to go with the best case scenario. So I was very much a worst case scenario. I can show off by telling you that at the first class in my lecture in my class this semester, I told my students that classes will be cancelled. So at the first week of classes, I told people that classes will be cancelled, and my student can attest to that. I think that actually the situation is probably not as bad as we think, because I think there is a lot of undetected disease going on. And I think that there is a good chance that we will be past the worst on it, at least this wave, in less than a month. That's sort of my best case scenario. One thing that doesn't really answer your question, I think one of the things where we have to be very careful, and I don't think that the models right now that inform policy take into account, is to take into account the fact that economic outcomes also have a big public health impact. So if people lose their job, if people lose their health coverage, they may die. And they may not have access to the medication that they need, they may not get the treatment that they need, right? So it's something to take into account. I don't know to what extent is this impacting policy right now. But my feeling, just from the fact that there are so many people sick around, all these anecdotal stories that I hear, my sister is a doctor in Israel, stories I hear from other doctors, there are so many people who have weird respiratory disease that is not corona, but it's treated somehow. My feeling is that it's much more widespread in the community. And this is a good thing, right? Because if it's so widespread, many people will get over it, they will get, recovered, they will not get it again, at least in this season, and we hopefully will be out of it in a month. Worst case scenario is all yours, Ankur.
Oh God. Yeah, I'm gonna abstain from saying the worst case scenario, but let me at least say some positives that, right now, not going to conferences, not doing all of this traveling, it's had an amazing impact already in the short term in, reducing our carbon emissions. So maybe it'll force us to rethink some of these things about how we've built up our lives. I think, let me, angle a little bit more on the worst case and say something else, which is that, I think we're going to get into trouble if we think that this is a random one-off fluke, that there are many different types of strains of coronaviruses that, have been predicted actually for a few years that they could make the jump to humans. So I think these kinds of things might end up not becoming a one in a century kind of thing. So I'm hopeful that at least now that these issues are on everyone's mind, we can all start to take a more sober look at what are the modeling assumptions that go into computational epidemiology. There are a lot of issues that we don't necessarily talk about, like the fact that these models are not open source. It makes it very difficult to understand robustness checks. But on my end, I certainly talk a lot to some of my family who have a lot of questions and debates about these kinds of things. And without people being able to play with these models and understand what these predictions mean, what these policies mean, how robust or not robust are these models, it's really difficult to have a positive and productive conversation about it that's not just grounded in fear and uncertainty and lack of knowledge. So I'm hoping that at least, there's some positive steps we can take research-wise, as community-wise, as reevaluating, some of these fields and taking a deeper dive.
Thank you, Ankur. Thank you, Elchanan. It's 3 o'clock. You have inspired us to come to the field. You have educated us. It was an awesome hour. I'm going to clap on behalf of everyone. You're both awesome. And for all of our audience, we are going to post-process this recorded talk, and we will let you know when the video is available. Thank you. Have a safe and healthy afternoon.